Hi. We will now figure out what the what the electric field is of an infinitely long line of charge distribution. So first of all, since we're going to be using symmetries here, what are the symmetries of this thing, right? First of all, you notice that if you do a rotation of space like this, using the line of charge as the axis, we find that the charge distribution is the same before and after the rotation. So therefore the electric field must be the same before and after the rotation. Also, what happens if we translate the charge distribution, let's say this way? Well, again, the charge distribution looks the same, so the electric field after such a transformation is to be the same thing as the electric field before. That means that if I take a point here, after that translation it would be somewhere over here, and if I look at the electric field there, let's say the electric field was like this before we do the translation at this point, and then it was like this, right? Then after the translation, this vector, a vector transform, would just be translated over, so it would look like this, and then you'd have the problem that before and after the translation they're not the same. So in other words, from this you can tell that before and after the translation it must just be the same vector moved over. So you'd have this, let's say in this, so it's the same basically everywhere. The vector's the same everywhere, because it's not only this translation, but it's any translation, small or big. So had it been only this much, the vector would have been here. So you find out that they're all the same vector at each point, at that sort of surface of translation or line of translation, which is along here, right? So if you look all around the thing, there'll be different lines like this in a circle around it. In a circle, not even just filling space like this, all parallel to him. And along those lines, since those are the lines that are preserved by translations, the field must be the same. The vector must be the same at each point along those lines. Okay. Now, if I let's see, what else? If I flip over a line like this, not a line, sorry, I should say a plane. So if I got a cutting plane like this, and I do a reflection, perpendicular reflection right over that plane, the charge distribution looks the same. But now, how does the vector transform? Well, if he was coming out of the plane like this before, then he would look like this after. So let's say this is vectors here coming out, at an angle, but coming out of the plane. Then after, they will look like this at an angle. So you see that that the vector field before and after this reflection is not the same, but the distribution is, and that can't be, so it should be the same. So in other words, we know then that the vector should be at this point right here should be contained in the plane between this and the point. In other words, between the line of charge and the point. If I get the plane that contains that line of charge and that point, the vector should lie in that plane, so to speak. You have to know what it means for a vector to lie in a plane, but anyways. So now, even though I draw this at a slant, I mean at a slant, but inside this plane right here. Okay? Alright, we know that much. Now, furthermore, look at this line right here. If we flip the line of charge over that line, again, it's the same before and after because the line of charge is infinite there. So we find that the vector field after flipping over that line should be the same. But we already know it's in this plane, and now we know that after flipping over that line, that's you know also in the same plane, that it would look like this. But it shouldn't look like that after the flip. So the only way the vector couldn't have been to an off angle like this, but the only way it could have been is like this. Okay? And by the way, you could have carried this argument on any sort of radial plane like this, right? And you find out then that the electric field is radially directed. Okay, so we know that much, that it's radially directed, and that along lines like this is the same size. So it looks like this. So it looks like that. Okay. Also, you know that upon rotations like this around this axis right here, the field before and after is the same. So that means that if the field is radial here like this, and at some other point here along the circle here, it was radially out like that, you know that these two must be the same size by the same argument as before. You know, had they been a different size, had this guy been this long here and this guy been this long here, after the rotation now, this guy translated over, it's that long, and the field here before and after is not the same. So the only way that it could be the same before and after is if they both had the same length to begin with. So we know now that on radial circles, right, and along lines like this, so basically on cylinders, the field has the same length, and we know that it's radially directed. Okay, and that's it. The actual size of the field on each of those cylinders, you'd have to figure that out by Gauss's law.